So our number system is called the denary or decimal number system. The DE at the beginning of it is short for dec, which stands for or means 10. So for example, in the word decade, 10 years, decagon, 10 sides. So what it means is that our number system has 10 digits, the digits 0 to 9, and it is in base 10. So to really understand other number systems like binary, which is what we're talking about today, it really helps if we first understand how our number system works. So to begin with, we're going to talk about exactly the hows and whys of our number system. So if we have a 4 on its own, a single digit, that just means 4 ones. We can count all the way up to 9 like this, 1, 2, 3, 4, all the way up to 9. But if we want to go one more than 9, we have a problem. We don't have any digits to represent anything more than 9. So this is where position comes into play. So if we have one more than 9, which is 10, we can use the column to the left of the 9 to record that we've counted up to 10 once. And then we put a 0 in there to say that it's no more than 10. So if we had, for example, 1 and 4, that means we've counted up to 10 once, and we've got 4 more ones. So if we were to record 99 and we wanted to go one higher, we need to add one more to the ones. However, we can't do that, so we bring it back down to 0 and say that we've counted up to 10 once more. However, we can't do that, so we go to 0 and we can use the column to the left of that. So this one in this column means that we've counted up to 10 times, which you will know means 100, but we want to formalise this a little bit. So if we draw out a table, like I'm sure how you learnt it in school, with column headings. So this first column heading is the ones. This column heading is 10 times that, so 10 times 1. This column heading is 10 times that, so 10 times 10 times 1. And then so on, this column would be 10 times that, so 10 times 10 times 1. So in school you will have probably labelled them 1, 10, 100 and 1000. But to more easily relate them to other number systems, particularly binary, we're going to write it slightly differently. So instead of 1, we're going to record that as 10 to the power 0. 10 because it's base 10, and power 0 because the power of 0 gives us 1. So in this column, 10, we can write as 10 to the power 1. The 10 times 10 is 10 to the power 2. And finally this column, 10 times 10 times 10, which you know is 1000, we can write as 10 to the power 3. And we could continue. So each digit is 10 times the value of the digit to the right. And hopefully you're starting to see that it is actually the position of the number that matters, the position of the digit within the number. So if, for example, I wrote the number 70913, working backwards along the number from starting at the 3, we can see that that means 3 times 10 to the 0, add 1 times 10 to the 1, add 9 times 10 to the 2, 0 lots of 10 to the 3, and then 7 lots of 10 to the 4. So if we added all these up, 3 times 10 to the 0, 1 times 10 to the 1, 10, 9 times 10 to the 2, 900, and 7 times 10 to the 4 would give us 70,000. So in total, 70,913. Of course, you already knew that, but now we understand the hows and whys of our base 10 number system, we can move on and apply that to a base 2 number system, to the binary number system. So the prefix of binary, bi, means 2. So like in bicycle, 2 wheels, or you bisect, you cut something into 2. So the binary system is base 2. This means it has 2 digits, so it only uses the digits 0 and 1. So like in our number system, we can count up to 1. So to count up to 2, we can use position. So if we're at 1, we want to add one more on. We don't have a digit to represent it, so we use the column to the left to say that we've counted up to 2 once, and then we've got no more units. So 1, 0, represents 2. So we can add one more unit onto that, which would give us one lot of 2 and one lot of 1. So that represents 3. But how do we get to 4? If we want to add one more onto 3, then we'd add one more onto the 1s, but we can't record that, so that goes back down to 0, and we add one more into the 2s column. But that we can't record that, so we put a 0 in there and say that we've actually counted up to 2 twice. So like in our number system, when you count up to 10 times, we use a 1 there. This is to represent that we've counted up to 2 times. So in binary, this is actually a 4s column, this is a 2s column, and this is a 1s column. So just like our denary system is base 10, the binary system is base 2. So we can do column headings as we did before, but this time, instead of it being 10, we've got 2. So this is 2 to the power 0, which is 1. This column represents 2 to the power 1, which is 2. This column is 2 times that, so 2 to the power 2, which is 4. And this column would be 2 cubed, which is 8. So every digit is 2 times the digit to the right, instead of our number system, which is 10 times the digit to the right. So if, for example, I had the number 11011 in binary, so we put a little 2 down there to show it's in base 2, it's a binary number. So we can start from the rightmost number, and we've got a 1 there. So that is our 2 to the power 0, so we've got one lot of 2 to the power 0. Move along one column, one lot of 2 to the power 1, no lots of 2 to the power 2. We're on this now, so one lot of 2 to the power 3, and the very leftmost one is one lot to the power 2 to the power 4. So 0, 1, 2, 3, 4. So then we can add them up. 2 to the power of 0 is 1, so 1 times 1 is 1. 2 to the power 1 is 2, so 2 times that. 1 times 2 is 2. No lots of 2 squared. 2 cubed is 8. And 2 to the power of 4 is 16. So if we add up all these numbers, 16, 24, 26, 27. So 11011 actually represents the number 27. So like we used a small 2 at the base of the number here to represent that it was base 2 or binary, we could actually write a small 10 at the base of this number here to show that it is base 10 or a denary number. So this 10 here and this 2 here don't do anything other than tell us what base the number is in. So now you've seen how it works. So as a quick test, pause the video and see if you can work out what the number 110111 represents. So 110111 would be 1 times 2 to the 0, 1 times 2 to the power 1, 1 times 2 squared, 0 lots of 2 cubed, 1 lots of 2 to the power 4, and 1 lot of 2 to the power 5. So 1, 2, 4, 16, and 32. Add them up. 15, 40, 55. So 110111 makes 55. If you didn't get that, check your workings, look back at the video, have another go. So that's all good. You now know what a binary number represents, but what if we want to go the other way? What if we wanted to represent 23 using binary numbers? So we can use our column headings. We've got our 1s, or 2 to the power 0s, or 2 to the power 1s, or 2 squareds, 2 cubes, 2 to the power 4. We could represent it as 23 ones, but of course we're not allowed to do that, we're only allowed to go up to 1. So we can use the next column. 23 divided by 2 is 11 remainder 1. So we can represent that as 11 lots of 2 remainder 1. So now we've got this 11 in this column, which is still too much because we're allowed to go up to number 1, but we can use the column to the left of it, which is 2 times more than that. So if we split the 11 into 2, that gives us 5 remainder 1. So this 11 we can represent as 5 in this column and 1 more in that column, and then we've still got the 1 on the end there. So now this column is okay, but this one is still too big. So we can do the same thing. Use the column to the left of it, which is 2 times bigger, so we can represent that as a 2 in this column, 1 in that column, gives us the 5, and then we've still got our 1s there. So 2, 1, 1, 1. We're getting there now, but this is still too big. So we can split our 2, and that gives us 1 remainder 0. So in this case, we can represent a 1 there and a 0 there, and they should all be 1s underneath there. So just to finish it off and check, we've got a 1 in this column, 1 divided by 2, we can't move it to the column to the left, that doesn't give us anything, and we've got our 1 remainder. The reason I've done this last one is there is actually a shortcut to this method. So looking from top to bottom in our remainders over here, and from right to left in our answer over here, we can see that the remainders 1, 1, 1, 0, 1 are used in our answer 1, 1, 1, 0, 1. So you can actually use this method and use the remainders to create the binary number. So hopefully you see how that works. And now as a quick test, why not have a go at trying to represent the number 33 using binary. So to represent the number 33, we can do 33 divided by 2, because we're in binary, so it's 2, which is 16 remainder 1. So we could represent that as a 1 in the 1s and a 16 in the 2s. But obviously 16 is too big, so again we divide that by 2, which is 8 remainder 0. Then that's still too big, the 8, so 8 divided by 2 is 4 remainder 0. 4 divided by 2 is 2 remainder 0. And then 2 divided by 2 is 1 remainder 0. And finally 1 divided by 2 is nothing, so we know we can stop, but we've got this 1 remainder. So starting from the top, that starts on the right, we've got 1, 0, 0, 0, 0, 1. So in binary, we can represent the number 33 using 1, 0, 0, 0, 0, 1. So to check that works, let's check out our working. And we've got, starting from this digit, that's our 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the power 4, and 2 to the power 5. So we've actually only got base 2, one lot of 2 to the 0, and one lot of 2 to the 5. 2 to the power 5, of course, is 32. 2 to the power 0 is 1. 1 and 32 make 33. So now you understand how binary works, let's pause the video, give yourself a quick test. So number 1, I want you to work out what the number 1101 is in our denary number system, so as a normal number. And number 2, I want you to represent 135 in binary. So pause the video and I'll give you the answers in a second. So 1101 was the binary number I asked you to calculate, question number 1. So let's work out what that is. So that's my 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So one lot of 2 to the power 0, no lots of 2 to the power 1, one lot of 2 to the power 2, and one lot of 2 to the power 3 is 1, 0, 4, and 8, and that gives us 13. So to represent 135 in binary, we need to work out each digit by dividing by 2. So 135 divided by 2, 67 remainder 1. 67 divided by 2 would give us 33 and one more. 33 divided by 2 is 16 remainder 1. 16 divided by 2, 8, remainder nothing. 8 divided by 2 is 4, without a remainder. 4 divided by 2 is 2. 2 divided by 2 is 1, with no remainder. And finally, the 1 divided by 2 is nothing, with 1 left over. So working from the top, 1, 1, 1, 4 zeros, and a 1 on the end. So 135 would actually be 1, 0, 0, 0, 0, 1, 1, 1. And you can double check your answers right by using the powers. We'd have 1 lot of 2 to the power 0, 1 lot of 2 to the power 1, 1 lot of 2 squared. That would be power 3, power 4, power 5, power 6. So 1 lot of 2 to the power 7. Of course, that's 1, that would be 2, that would be 4, and to the power 7 would be 2, 4, 8, 16, 32, 64, 128. So add them up, 132, 133, 4, 5. So we know that we're right. Good job. This applies to any number system, so octal, hexadecimal. If you want to watch a video on that, I'll shortly have one. Good job.